Hey there, everybody. Okay, let's get quick right into it. This is going to be Chemistry Unit 2.3 notes. These are notes that we're going to be taking in class. These are fill in the blank notes. And just so you are aware, you're probably going to hear a bell in this video as I'm recording this during a passing period. So just be ready for that. Okay. So let's just get right into it. So this set of notes, we're going to be blazing through 2.3 and also blazing through 2.4 notes. We're going to be going straight through them, practicing them a little bit, and we're going straight to the test next week. So a lot of this stuff is stuff you should already know. We're reminding you what it is, maybe expanding upon some things that you know and that you've heard of, and defining things maybe you didn't know the definitions to, trying to apply them more or less to the ideas of matter. So, okay. So we've talked about, you've probably either remember matter from, let's face it, actually, you should remember matter from all your science classes. Matter is matter. It is anything that has both mass and volume. It is material. It's things that you can touch. It's energy. It's the desk that you're sitting at. It's the carpet you're standing on. It's the clothes you were wearing. It is you. Everything is matter. And so we have to remember that matter is anything that has both mass and volume. Okay, well, we have to then define what mass is. Well, mass is the amount of matter found within an object. So we've measured mass already in class. We've measured the masses of graduated cylinders with water in them, powdered materials, solid materials. It is to find out how much stuff is in a thing. Okay, the amount of matter in an object. Matter is more or less matter is the scientific word. Stuff is the street word. It's the colloquial term for matter. It's stuff. Okay. Well, there's also volume. So, what does volume have to do with mass? Well, we'll get to that in this next little definition. But volume is the amount of space that an object takes up. So mass and volume are two different things, obviously. They're measured with two different kinds of units. They represent a measurement, two different kinds of measurements of an object. But volume is the amount of space an object takes up. It's the amount of space that matter, a particular amount of matter takes up. Okay? So what do these have to do with one another? Well, when we combine them, we have something that's referred to as density. Density is the amount of mass of an object that is packed into a specific amount of space. How much mass do you have in a particular volume? Or at a particular volume, in or at a particular volume. So now we calculate density. We typically go into density now just because, again, similar to the set of notes from last week, because of COVID, we normally would go into what density is and understand it better. Here's another place where you just need to know the definition of it for the test. You need to know and to be able to kind of explain it in your own words. And realistically speaking, it's pretty simple. It's how much stuff can you fit in a particular amount of space. Okay, how much mass can you fit in a particular volume? That's density. Okay, and a good way to remember that is thinking about maybe two objects that are the same exact size but have two different masses. So, as an example, let's see if I've got something close to me here. There's that bell. So maybe as a good example, my phone and my calculator here are roughly about the same size. Okay, they have approximately the same amount of volume as one, or the same volume between the two. Okay, now obviously you can see that there is a difference between them. Okay, calculator being a little bit bigger as far, or at least taking up a bit more volume here than my phone. But idea being, you can have two things that have the same volume. Okay, but of course, as we know, and especially if you hold these yourselves, you would see that my phone has more mass in it. Why does it have more mass in it? Well, it's because it has more parts. It has a larger battery. It has more screen components. It has a more rigid frame. there's a number of things that make this, my phone, have more mass. So using this, we can think of, okay, well, we can have the same volume, but we can have a different number of mass. How do we represent that? And the way we would represent that is using density. How much stuff can you fit into a particular amount of space? Or at least how much stuff is there in a particular, amount of space. And that's density, okay? Okay. Now, of course, again, we would normally go into density, but we're just going, it's just something you need to know by definition, not so much in practice. Okay, so states of matter. So now this is, again, this should be, for the most part, this should be review. States of matter, plasma, the states of matter you should be familiar with. It is something that you have worked before either in physical science or you have worked on it in middle school. It's something that has been repeated multiple years. States of matter are the different states that matter can be found in per a particular environmental condition. It's a lot of fancy words to say that matter can be in a particular kind of way when the environment is in another particular kind of way. So, okay, maybe let's get more specific. So plasma. Plasma is one particular state of matter. And now plasma, whether we think of science fiction movies, TV shows, whatever it be, plasma or blood, just understand that's a different kind of plasma. Plasma is a particular state of matter past gas. Okay, so this is, you would argue, is the highest state of matter as far as energy is concerned when it comes to states of matter. So this occurs at extremely high temperatures. Plasma does not have a definite shape nor a definite volume. So meaning you really can't put plasma can't be put into a graduated cylinder. You cannot measure it by tick marks. You cannot measure it by the amount of space it takes up because it doesn't really hold a shape. It cannot be contained within a specific area in order to calculate it for the most part. Okay. Now compare that, and as examples of that, that's the interior of the sun. It is found at lightning strikes. So, meaning that lightning strikes for the most part when you have that crack of lightning. That lightning itself for a split second is a form of plasma. Okay. I'll get to this stuff over here in just a bit. Okay, so gas. So we start with plasma. We work our way down to gas. Gas has no definite shape or volume, but it does not occur at the extremely high temperatures like plasma does. Gas is more or less like it says here. It's matter that has no definite shape nor definite volume. Can you? But Mr. Sheelan, can't you put a certain amount of oxygen into tanks, like say for scuba? Yes, you can. The only problem is that we don't measure the volume the same way we would for a liquid. So if you were to pour water into a graduated cylinder, you can measure exactly how much water you have in that graduated cylinder. You cannot do the same thing for a gas. The way you would have to measure the gas for its volume is more or less through pressure. So it's not exactly the same thing, and it's think of it almost as if we're forcing the gas into a particular kind of way in order to measure it, where with like a liquid or a solid, we can just measure it as is. It's a little different with gas. So examples of gas, so at room temperature, that's oxygen, carbon dioxide, that's nitrogen, that's helium, floating around, bouncing against the walls, atoms just kind of floating around. There's a lot of space between the atoms. We should remember this. And they're just kind of floating around, okay? So think of it in this way. When gas is like in every person for themselves kind of dodgeball. So people are moving back and forth. They're avoiding one another. They're bouncing off one another. They're for the most part, I guess you'd think the dodgeballs being in that way is that the dodgeballs are thrown in every direction. They're bouncing off one another, and they're just kind of floating in the space. Okay. Now a liquid. A liquid has no definite shape, but it does have a definite volume. So again, think of water within a graduated cylinder. Sure, you could say that oh, well, it's holding the shape of the cylinder. That's true. Remove the cylinder, and I'll guarantee you it does not hold its shape, okay? Because if you remove that cylinder, it will fall to the ground. Gravity will take its course, and it will pool onto whatever surface that it was sitting on previously. So it doesn't have a shape, but it does have value. We can measure it. We can just toss it into something, and we can measure it as is. We don't have to manipulate it in a particular way to measure it, okay? And of course, examples like that, at room temperature, that would be water just sitting there. It'd be like mercury, hydrogen peroxide, gasoline, those kinds of ideas. Think about how those sit in bottles. Think of how those sit in glasses. That's a liquid state. You can also think of liquid states as hallways during passing periods. So more or less like the shape of the flow of the students. Yes, you are contained within a particular space. Like if you think of the whole population of students moving throughout the hallways, you have a particular shape, you do not have a particular shape, but you have, we could measure, like you're contained within an area, and we can measure you within that contained space, okay? And then there is the solids. So solids have definite shape, they have definite volume. So at room temperature, that's gold, that's silver, calcium, iron 2 oxide, that's rust, plastics, woods. So as an example, think of yourself just sitting at a desk. You're sitting there, you're not really moving. I can for the most part, you have a definite shape in relation to the seat you're at, and you take up a very particular set of or number of value or a particular number when it comes to volume. So think of it in that way. Now, I told you I'd get to this over here. Oh, and I forgot about the last one, sorry. Then this last one is somewhat new, or at least somewhat new, and it's in the fact that we can somewhat observe it, or at least calculate it. So it's called the Bose-Einstein condensate. So the Bose-Einstein condensate has definite shape, if you want to call it a shape, and it does have volume. Now, the only thing is that this occurs at temperatures close to absolute zero. So, just so you're aware, absolute zero is the temperature in which the temperature Kelvin has reached 0 degrees, which arguably has never been observed. It is something that's calculated, but it is not something observed. We were able to extrapolate data to show a trend towards absolute zero, but it's so cold and it is so lacking in energy that it's difficult to accurately, or it's nearly impossible to measure, at least as of right now. So, what does it mean to have a definite shape and volume? Well, for the most part, what we see, or what scientists were able to calculate and to observe, because it's not at absolute zero, but it's pretty close to it. More or less, this is what happened. Is that scientists were measuring? We'll say that the scientists were measuring a particular solid, and the solid, we'll say, was some sort of atom. And we understand that atoms and solids, liquids and gases are arranged in a particular way. So a solid looks like this. So you've got like little itty bitty, teeny tiny packed atoms, all super close and packed together. And they're sitting there and they're vibrating. They're sitting there and they're vibrating inside of the solid, inside the space provided for the solid. Whereas in the liquid, there's a bit more space. They're moving a little bit. They're still bouncing against one another, and they still, are connected to one another. But for the most part, they're fluid. They're moving around, bouncing off one another. Okay, and then you've got a gas here, and the gas is where you've got, there's a lot of space between them, and they're bouncing off each other. They're just moving, flowing through the space, all that good stuff. Well, what happens when we get down to a Bose-Einstein condensate is that when the temperature reaches such a low degree, and you have to remember this because as temperature goes down, so if we start up here at plasma and we decrease temperature, we see that, or what we do see, what scientists see is that as you decrease pressure, or temperature, let's say that's starting at gas, if you begin to decrease the temperature, what you begin to see is that you have, less temperature means less energy means less movement. So you would have these gas particles would be moving, they'd be getting closer together, they'd be moving slower, they wouldn't be moving at such a fast rate. Liquid materials, as we know, similar to, or at least for the most part, like water, freezes. Okay, now not all liquids do that, but a lot of liquids freeze at a particular temperature and become a solid. As you keep going down and down and down, what happens is that, idea being is that you are limiting the space in which something can move. You're limiting the motion that they would otherwise normally have. And it reaches a point here where you have an atom that would just be sitting here, okay? And you've put it at such a low temperature that it begins to vibrate in a single spot, and it more or less becomes a wave, and it's actually really cool. And it radiates these waves out from the center. It radiates these waves out from the center pretty much at a similar, or between different atoms, between different materials at similar rates. And it becomes this kind of wave pattern, kind of solid material that's just sitting there vibrating just intensely. I'll link a video that'll explain what this is a whole lot better than what I just did, but for the most part, that's what it is. It almost transforms into a wave, which is kind of unheard of. It's kind of strange. And especially we don't think of all matter doing that. We may think of light being able to do that, where a light can travel both as a wave or as a particle, or it can travel as in wave form. So which we get into a little bit in chemistry, more in physics than anything. But anyway, so yeah, watch the video if you're a little confused on what this is. I'll link to that video. As an example, this is superfluid, so cold liquid helium. So at a certain point, we have helium gas. You decrease the temperature so much, and you condense it so much that eventually becomes a liquid. And then once it becomes a liquid, it more or less does this. It's like a uniform wavelength or wave-like pattern or shape. Superconductors, nucleons inside a neutron star. Just need to know not exactly, or I'll just say this, why don't you just go ahead, see what a superconductor is, see what a nucleon is, okay? Don't need to know it for the test, or at least the definitions of both of these, but you have to understand if I ask for an example of a Bose-Einstein condensate, you should be able to give me one of these, okay? So, all right, well that's the notes for this, guys. Actually, no, it's not. One last thing. So here's a chart. So again, here, this chart is over here is proportionate and follows the pattern of the terms we see here. So the higher the heat, the higher the energy. The more energy, the more heat we have. Okay, turns to plasma. Less energy, less heat. We go down the scale, from plasma to Bose-Einstein condensate. Okay, particle movement. The faster it is, the more it spreads out. Yeah, that's plasma, and that's up here. That's from if we're moving up in scale. That's moving from the Bose-Einstein condensate up to plasma. But as far as particle movement, the slower ones are down here. Okay, because think of solids. Solids don't really move all that much. They just sit there and they vibrate, but they don't have a lot of movement because that's how they keep their shape. That's how they keep their form and have a definite shape and volume. So that's what this is over here. It's to say the higher up we go on this list, the more energy and the more heat, the faster the particles move. But the lower we go on the scale here, the less energy and the less heat, the slower and closer together these guys, these atoms, these molecules are. Okay? All right, well, those are the notes. If you have any questions, make sure you ask me, whether that's email, remind, in class, whatever it has to be. Other than that, I will see you guys in the next video.